Hi, welcome to part 2 of lecture 8, Triple 107. We'll still talk about the noise in analog modulation techniques. Okay, still won't leave that topic. And in this lecture, we'll talk about the performance of full AM, FM, and PM. Okay, so the last lecture, we talked about how to evaluate the different modulation schemes. Okay, so evaluating them, we need to have a reference SNR and your post-detection SNR. Okay, and with that, you can use the figure of merit to compare the performance of your different modulation schemes. And we analyzed the coherent detection for both SSB and DSB-SC and found out that they have the same performance against noise. Now, let's look at envelope detection. When you have when you have a full AM signal, we use the envelope detection to this simple envelope detector to demodulate and recover the message from an AM wave. So recall an AM wave, it can be expressed in this way, and it has already been uh, impeded by uh, narrowband noise. Okay, and we can decompose this into its in-phase and quadrature components. Okay, so we can get the pre-detection SNR of an AM signal. So the power of an AM signal, recall, is equal to this expression. The bandwidth of AM signal is the same as DSB-SC, which is equal to twice the message bandwidth. And the narrowband noise is equal to N0 times the transmission bandwidth, BT. Therefore, the pre-detection SNR is equal to this expression right here. So you just divide this by N0 BT. Okay. So the post-detection SNR, this gets a little tricky because the envelope detector outputs the envelope of your received signal. Okay. So what you get at the output is actually equal to the magnitude of this AM of T, or the envelope, the complex envelope. And to get the magnitude of your complex signal, you have to get the square root of the sum of the squares of these, the in-phase and the quadrature component. Okay, you're actually getting the magnitude M of T. So this is the recovered message. So the goal is we want to recover this one, but because of noise, after the envelope detector, we get this expression. Okay? So if the signal is much larger than noise, then we can approximate that to have this expression right here. Only the in-phase noise is present, and the post-detection SNR can now be expressed as this equation right here. So why did the constant term disappear? The constant term disappeared because it does not carry any information. Therefore, we remove it using a DC block. Mu here should be adjusted to prevent overmodulation. Therefore, mu has a maximum value of 1. And this is only valid for a high SNR case. So we approximated that by making this disappear because it's very small. Okay. So the reference SNR can be rewritten as this. Where did this come from? Well, recall the process of getting the reference SNR. We have a signal here, the message signal with the same power as the transmitted signal. And then you have a noise signal. Then you pass it through an LPF with the same bandwidth as the message. Okay. So you have, again, the message signal plus the noise signal. The power of the message signal is equal to the message of the transmitted, the power of the transmitted signal. That's AC squared over 2 times 1 plus mu squared, the power of the message. And the noise is still the same, the power of noise is equal to N naught times W. Okay? So that is where this came from. So this is the reference SNR, and this is the post-detection SNR. So we can now get the figure of merit. It's equal to this expression right here. Okay? And just a note that mu squared PM is always less than 1. Okay? Thus, the figure of merit of AM is less than 0.5. That means that its noise performance compared to DSB-SC and SSB is inferior because at least half the power is already contained in the carrier. It's allocated to the carrier, at least half of the power. And this is one drawback of using the carrier. If we want to use the carrier, yes, we have a simple detection using the envelope detector, but the price for that is that we sacrifice some noise performance. So it's not just the bandwidth, it's not just the power, but even the noise performance of AM is already compromised by already using a carrier. And this is also true if you compare VSB to VSB plus the carrier. Okay? You sacrifice some noise performance for a simpler detection scheme. Okay? Right. So after that, now we talk about the noise in FM detection. Okay? So the block diagram for an FM receiver looks like this. Okay? This is the first part here is your down conversion, and the next parts here would be, sorry, forgot to include this, but this will be your demodulator. Okay. So let's look at the pre-detection of FM signals, which is right here. Pre-detection, the FM signal has the following expression, okay, where your phi m is equal to, is dependent, is linearly, it's linearly dependent on the integral of the message. So this is an FM signal. So recall the property of angle modulation, constancy of transmit power. There's really not, doesn't matter if you have an FM or PM signal, but the pre-detection SNR of FM is dependent on the power of FM, which is just equal to AC squared over 2, and that's it. It does not depend on the message power at all. And the noise bandwidth is equal to N naught times BT, where BT is equal to the bandwidth using Carsons Rule. Okay? So, in the post-detection of SN signals, of FM signals, since the noise has an in-phase and quadrature component, we can express it again in the following term. Instead of expressing it using the cosine and sine components, we can express it as having some amplitude and some phase that varies with time, and using that, this is from the identity of how we define the in-phase and quadrature components as components of a vector. Okay, so this is where this equation came from. This is where this equation came from. And the noisy FM signal can now be rewritten as such, right here. Okay, and since they are phasors, we can solve for their resultant by using vector analysis. Okay, so with that, we can solve for the magnitude of your FM signal. Right. So with this, the instantaneous phase of the signal, which is this one, can be taken from this expression right here. Since we're trying to detect an FM signal, we're trying to get its instantaneous phase from phase discrimination. Therefore, the instantaneous phase is equal to this. Okay. If we assume that the carrier to noise ratio is very large, then this expression, this phi m here, this expression rather, can now be simplified into this. So if AC is very large, this term disappears, and we'll be left with this term, right here. So just note that the tangent inverse of x is approximately x for very small values. Okay, and since AC is very large, then we can simplify that. Okay. So now the instantaneous angle can now be expressed as this. And if we feed that into a discriminator, we get this value for the received signal. And this will be your noise term. Okay. So what happens to the noise? The output here is actually the derivative of the noise. If we convert that to its frequency domain by using the properties of Fourier transform, a derivative is equal to multiplying j2 pi. Right? Equivalent of multiplying j2 pi f. It means that the frequency spectrum of noise, the power of noise increases as you move away from the origin. Right? Therefore, if your bandwidth is larger, the larger the effect of the noise. Okay? So the corresponding spectral density looks like this. It's actually quadratic. Okay? So the power spectral density will now be equal to this after discrimination. Okay? So now we get the post-detection SNR. So we just get the area under the curve of the power spectral density, and it's equal to 2n naught omega cube, sorry, w cube over 3ac squared. So you just get the area of this under the curve. So get the area of this under the curve. You get the power of the noise after post-detection. And now we can get the SNR. So the SNR at post-detection is equal to this. And using the figure of merit analysis, how did we get this reference SNR? So this reference SNR, again, we use the same process as before. And we use here an LPF with bandwidth W, which is equal to the bandwidth of the original signal. Okay? So the bandwidth of the original signal, W, results in still the same message, but the power of the message is equal to the power of the transmitted FM wave, which is AC squared over 2. Okay? And then the power of noise is N naught W. Therefore, the reference SNR is equal to AC squared over 2 N naught W. So if we get the figure of merit, this divided by this, simplifying that, we get the figure of merit equal to this, which is equal to 3 times the deviation ratio squared, which was defined when we discussed Carsons Rule. So what does this tell us? The performance of FM, okay, the performance of FM will increase if the deviation ratio increases. However, when we're deriving this, we can only see that it's valid for high SNR values. So that means there's a certain minimum threshold value wherein your derived expression for post-detection SNR is still valid. And if you go below this threshold, well, your figure of merit, your post-detection SNR will become unpredictable. Okay, and that is what is very large, maybe around 10 dB. Okay, if the signal power is at least times 10 the noise power, then we can already say that you're already above the threshold. Okay, and we compare this to AM. As you can see, FM has superior noise performance compared to AM signals. If you increase the bandwidth, which is directly related to the deviation ratio, so if you increase the bandwidth of an FM signal, you have superior noise performance. However, it degrades at some point because of this power spectral density. Okay? So we can actually reduce the effect of noise using the emphasis filtering. So this is one of the good things about the FM signal. Okay, if we use the emphasis filter, since there's severe noise degradation at high frequencies, if we de-emphasize the high frequencies before we process the signal, then we are reducing the effect of noise. Okay? But doesn't this introduce distortion to the signal? Okay. So it would introduce distortion to our message signal, of course. If you have this type of filter that does not satisfy the that does not satisfy the distortionless conditions rather, then what's the point of using a de-emphasis filter? Well, we can use a pre-emphasis filter that will equalize the effect of the de-emphasis filter. So the pre-emphasis filter will have an inverse frequency response to that of a de-emphasis filter. Okay, so there's an example in the book for that. Okay, so how about the noise effects on your phase modulation? So property 1 applies both to FM and PM, therefore they have the same pre-detection SNR. And due to the similarities of your FM wave and PM wave, we can use the instantaneous angle definition, but with certain differences. At high SNR, your instantaneous angle will be will simplify into this expression. And this phi m of t is defined by the message signal. Okay, and this signal right here will just be equal to your quadrature noise divided by your carrier amplitude. So now we can solve for the post-detection SNR. The post-detection SNR is equal to this. So it's the power of the message signal, Kp m of t. So that's Kp squared times the power of your message. And the noise power is equal to N naught W, divided by 2 N naught W rather, divided by AC squared. Okay. So dividing this with that, you get the post-detection SNR, the same analysis to get the reference SNR of your phase modulator. We get a figure of merit that is equal to the deviation ratio squared. And the same effect applies on FM or on PM. If you have a higher bandwidth, a higher deviation ratio, then you have a higher, more superior noise performance according to the figure of merit. So the trade-off here is that you sacrifice more bandwidth for better noise performance. And that is true on FM and PM over your AM modulation. A trade-off is that it's very complicated to implement an FM and a PM system compared to an AM system, as you can see. For an FM and a PM system, you need a lot more just to build them and make them work. Okay? And that's the end of this lecture. So if you have any questions or comments, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.